the thing that you guys want to remember in this discussion is the Aufbau principle. Aufbau is just a building out. And building out simply means that if you take the electron configuration of hydrogen, then we can build the electron configuration for helium starting from the electron configuration of hydrogen. If we take the electron configuration for oxygen, okay, then we can get the electron configuration from oxygen from building it from the electron configuration of nitrogen. It's always one electron more. Hund's rule tells you the restriction in terms of the electron configuration. Pauli exclusion principle, we actually talked about that already. It says no two electrons in an atom has the same set of quantum numbers. That is, each electron in an atom has a unique identity. That's the Pauli exclusion principle. And then I want to talk to you about diamagnetic and paramagnetic. Diamagnetic is when in an orbital, two electrons are paired. Paramagnetic means that in an orbital, these electrons are unpaired, okay? They have the same spin, and so they're not matched up. So make sure you understand this by the time we leave this section, because you're going to be quizzed on this in your next assessment. So this just tells you how are the electrons of an atom's arranged, what are the shells, how they liken to a hotel, their orbital. I'm going to give you an analogy there. What is the importance of the valence electron? And this right here is the key to chemical reactions and molecular structure. The valence electrons, okay? So, prelude to the electron configuration. Let's take a look at this right here. See if I have my, okay, that's not showing up. So let me go ahead and pull it out from my file and then show it to you from there, okay? I actually have that file somewhere. And this will give you an idea of what I'm talking about or what we're talking about when we do electron configurations. So I'm going to just do this and then put it right here. This is the movie that would be here, but for some reason, my PowerPoint on my iPad is not working in terms of the voiceover.
In the modern theory of the hydrogen atom, or any one electron ion, all subshells with the same principal quantum number n have the same energy. Theory tells us, however, that in atoms containing more than one electron, the repulsive interactions of the electrons with one another cause subshells of the same principal quantum number to differ in energy. The one electron in the hydrogen atom, in its lowest energy, or ground state, occupies the 1s orbital. In helium, atomic number 2, there are 2 electrons. Where does the second electron go? The first rule is that electrons occupy the lowest available orbital. The second rule follows from the Pauli exclusion principle. Any orbital can hold, at most, 2 electrons of opposite spin. These rules tell us that in helium, both electrons occupy the 1s atomic orbital. With increasing atomic number, the electrons occupy orbitals of increasing energy. With carbon, we encounter a new question. Because there are 3 degenerate 2p orbitals, that is, orbitals of equal energy, Hund's rule tells us that with 2 or more orbitals of the same energy, we should place electrons singly in each, with parallel spins until all are half full. With nitrogen, we arrive at a half-filled subshell. A half-filled subshell is associated with special stability. As we come to oxygen,
let me pause there.
All the vacant.
Let me pause there because you notice how each electron configuration is built from the previous one. That's called the off-bar principle. When you build the electron configuration of the next element from the previous one, you're building out. That's off-bar. The other thing I want you to note is Hund's rule. It basically tells you that when you have a choice of putting the electrons, that these all have the same energy. The fact that they all have the same energy and at the same level, they're called degenerate. Okay, Degenerate. These are degenerate orbital. These right here are degenerate to each other. These right here are degenerate to each other. These right here are degenerate from each other. But this orbital and this orbital are not degenerate because they have different energies. So degenerate orbitals have the same energies. So when you have degenerate orbitals, you can put the first electrons anywhere, but your next electron better be in another orbital that's empty with the same spin. And then if you have a choice, you have a third electron to put in, you need to put it in an empty orbital. That's obeying Hund's rule. They have to have the same spin, they have to go in separate orbitals. And then when you're forced to pair them up, then you give it an opposite spin, okay? Like here. So that's basically what we have right there in terms of that. So let me go ahead and continue on because I really wanted to explain, first of all, the idea of the off-bar, the idea of degenerate, and the idea of Hund's rule, okay? So hopefully you got that.
Orbitals of equal energy. Hund's rule tells us that with two or more orbitals of the same energy, we should place electrons singly in each, with parallel spins until all are half full. With nitrogen, we arrive at a half-filled subshell. A half-filled subshell is associated with special stability. As we come to oxygen, having used up all the vacant 2p orbitals, we must pair electrons. With neon, we come to the end of the first row of the periodic table, and the stable octet of electrons in the outermost shell.
Notice it said, with neon, we come up with a stable orbital, and that stable orbital has to do with the fact that all the let's see, right here, all the orbitals in the second shell are occupied. The S is occupied to the maximum. The P is occupied 2 electrons apiece. That's why neon is a noble gas, because there are no empty rooms there for the electrons to pick up. It's very stable. If you take a look at oxygen, oxygen here has 2 empty slots. It can pick up 2 electrons. That's why the most stable charge of oxygen is -2, because when it can pick up 2 electrons and fill those 2 holes, it's somewhat stable. So again, you can see how the electrons configurations are important in terms of how the electrons give up electrons and pick up electrons in order to get the same number of electrons as a noble gas. So let me go ahead and move on, okay? And this is shells and orbitals. This is your first shell, you have an s orbital. This is your second shell, you have an s and a p orbital, and the p orbital has 3 types. This is your third shell, you have an s, a p, and a d, and notice that the energy goes up. In the second shell, the p orbitals are higher in energy than the s orbital. In the third shell, the d orbitals are higher in energy than the p, and the p is higher in energy than the s. And this is your fourth shell. Notice you have an S, a P, a D, and an F. These are your S, these are your P's, these are your D's, and these are your F. Notice, however, that the S orbital, the 3s, this is the 4s right here, is actually lower in energy than the 3D. This is your 3D. And that's going to be important once we do electron configuration. Okay, that's going to be important. Why is the 4s orbital lower than the 3D? It has to do with the fact that the electron in the 4s orbital, it's going to look like this: 1, 2, 3, 4. The electrons can be found in the nucleus. Because it can be found in the nucleus, that means it's got extra stabilization. On the other hand, oops, let me go back. On the other hand, where's my diagram here? Sorry, I don't think I did a slideshow. On the other hand, what happens is, let me go back. On the other hand, what happens is that in the the d orbital looks like this. The d orbitals here don't have any probabilities finding on the nucleus, and so it's not stabilized by that. That's why your s orbital, 4s orbital, is lower in energy than your 3d. Even though the 3d is in the third shell and your 4s is in your fourth shell. Again, it's a complicated picture. The relative energy for the shells are the following. What we have is, this is your S, 1s, this is your 2. Notice how you have an S and a P. This is your third. You notice how you have your S, your P, and your D. And this is your fourth, fifth, etc. But notice how your 4s is lower in energy than your 3d. Not by very much, but still lower. Not very much, but still slightly lower. Okay? You want to keep that in mind, because once we get to the electron configuration of scandium and elements in the fourth shell, the fourth period, you're going to see why that's the case. If you want to know about the filling order, you can think about this mnemonic device. The filling order is 1s, 2s, 2p, 3s, 3p, 4s, 3d, 3d, and then 4p. Okay, 3d, this is 3d, and this is 4p. So this particular diagram, and it's in anywhere in the internet, tells you how the filling order is, but it actually parallels this filling order: 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s. So that's the filling order of how the electrons fill from the bottom up. Okay. So again, these arrows show you the filling order. Here's another way of remembering it. And as much as I'd like to tell you that these are good mnemonic device, your best mnemonic device is actually the periodic table, and I'll orientate you with that. So let's take a look at the electron configuration in relation to the quantum numbers. This is hydrogen all the way to neon. Okay, hydrogen has 1 electron, it's found in the s orbital. Helium has 2 electrons found in the s orbital. Carbon has 6 electrons. 2 of them are found in the s orbital, 2 of them are found in the 2s orbital, and 2 of them are found in the 2p orbitals. And notice how Hund's rule is obeyed. They go into separate orbitals. Okay, they go into separate orbitals with the same spin. This is nitrogen, 1s2, 2s2, 2p3. And remember, when we have the p orbital, that's L equals 1, -1, 0, and +1. These represents px, py, and pz. That's why there are 3 types here. There are 3 suborbitals. Each one of these represents a px, a py, and a pz. So this is your hydrogen, this is your helium, and this is what it looks like in terms of the filling. That's your hydrogen, that's your helium. This is your lithium, this is your beryllium. Let's take a look at how that's filled. That's your hydrogen, that's your helium, that's your lithium. Notice I put the arrow upside down. It doesn't have to go right side up. It could be upside down, but your next one better be a different orientation. Okay, so that's beryllium. Notice how the electrons are paired. That's what we call diamagnetic. So that's diamagnetic. All the electrons are paired. So beryllium is a diamagnetic chemical. Let's take a look at the next one. This is your boron, carbon, and nitrogen. Notice how Hans Rho is working on carbon. Look at that, the fact that these electrons are unpaired. That tells you it's paramagnetic. This too is paramagnetic. This too is paramagnetic. They all have unpaired electrons. The most paramagnetic of the three is nitrogen because it has the most number of unpaired electrons. The more unpaired electrons you have, the more degree of paramagnetism you have. So let's take a look at boron through carbon. That's hydrogen, helium, lithium, beryllium. That right there is boron. Notice I put it right there. That right there is carbon. I didn't have to put it in the next orbital here. I put it in a different orbital, same spin, Hans Rho. And that right there is nitrogen. Notice that there are 3 unpaired electrons. If we go back, that's carbon. It's got 2 unpaired electrons. That's boron. It's got 1 unpaired electron. So they're all paramagnetic. That right there is beryllium. It's got 2 paired. It's got a paired electron. That's not paramagnetic. That's diamagnetic. That's diamagnetic. Okay. So again, trying to draw you a picture of what's going on in terms of this. Let's take a look at oxygen, fluorine, and neon. Oxygen, fluorine, and neon, we have the following.
I remember last year, we could all test this. I remember last year.
You guys okay? I'm gonna have to, someone's talking in the background. Let me move you guys, okay?
Can I grab a couple things? Any drinks? What kind of drinks do you want? Puddles?
Sure. Not believe me. Not first. No, stop it. They got 1 or 2 records. They apologize. Hold on! Whoa.
Dr. Garces? I think your mic is muted.
Sorry, thanks. Let me go back. Thanks for letting me know about that. Sometimes I forget what the different controls are. So we're looking at the electron configuration of oxygen through neon, and we're building up from lithium to beryllium to boron to carbon to nitrogen. And then for oxygen, what we have here is we're now forced to pair it up. But notice how you still have 2 electrons here that are unpaired. So this oxygen is still a paramagnetic chemical, even though it's less paramagnetic than nitrogen. Nitrogen's the most paramagnetic. It's got 3 unpaired. Oxygen and carbon. Carbon has 2 unpaired electrons as well, have the same degree of paramagnetism. 2 unpaired electrons. Now we come to fluorine. Notice that fluorine has 1 empty space there. No wonder fluorine and all the halogens prefer a -1 charge, because if it can pick up another electron from, say, a different atom, then it'll have the same number of electrons as a noble gas. And the neon electron configuration is the noble gas. So that basically tells you that neon is diamagnetic right here. Okay, so again, we've built up this quantum mechanic model of the S, P, D, and F, and then we show how it relates in terms of the electron configuration. So hopefully what you can see is make that relationship. And you're going to have to do that in Chem 200, because we really get into more details in Chem 200 in quantum mechanics. Here, I'm just sort of painting you a superficial picture of how these things relate. Okay, so all that is nice and all that is good, but when it comes down to it, the best way to do electron configuration is not through this diagram or not through these mnemonic device that I gave you, but it's through the periodic table. And that's because the periodic table will always be something that you have in any chemistry assessment. Okay, and so what I want to do is I want you guys to see how this picture that we painted in terms of quantum mechanics relate to the periodic table. This is your periodic table, just the bottom portion. Notice I colored this in yellow. The reason why I colored this in yellow is because the electrons for these elements are all going into the s orbitals. They're all going into the s orbital. And so I like to call this the S family. Notice that these right here are pink. And the reason why they're pink is because the very last electrons that you place for these elements are all going into the d orbitals. D orbitals. And this is the 4th shell. This is n equals 4. And n equals 4, your values for the other quantum number, L, can be 0, 1, 2, and 3. Okay, that means that you can have s orbitals in here, you can have p orbitals in here, you can have d orbitals in here, and later on you can also have f orbitals. Okay, but those are much more complicated. And then your m sub L, that's going to be 0 for L equals 0. That's going to be -1, 1, 0, and +1 for L equals 1. Those are your 3 types, PX, PY, PZ. That's these right here. Okay, and then for L equals 2, you got -2, -1, 0, +1, +2. Those are your 5 types. That's these right here. These are, there's a total of 10 in here, okay? And the 10 represents the 5 different types of d orbitals. And each one of these d orbitals can fill a maximum of 2 electrons for a total of 10 spots. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So do you see how we're putting together the relationship between the periodic table and quantum mechanics? And that's probably the best thing in terms of this right here. I don't know why I can't get this thing to erase. Okay, let me get out of here real quick because I'm not in the slideshow. That's the problem, is that I'm not in the slideshow. Here, I got to do this. Okay, now I'm in the slideshow. Except it keeps doing that. There. So what we have now is the S, 1S, 2S, 3S. This is your 2S, 3s, 4s. This is your 2p. This is your 2p5. This is your 2p6. And this is the diagram I want. These are your S block. This is your D block. This is your P block. And this is your F block. And we don't have a G block yet because we don't have that many elements. And what I want to show you here is the following, okay? What I want to show you here is the following. I'm going to clear this. This is your hydrogen. It's got 1 electron. This is your helium, 2 electrons. This is your lithium, 1 electron. So your lithium here is built up from the previous one, 1s2, 2s1. This right here is your magnesium, okay? It's got an electron here. It's got 1s2, 2s2. And then we go to 3p1. In this second shell, we've got a 3p1, we've got a 3p2, that's your carbon, we've got a 3p3, that's your nitrogen, and so on and so forth. This right here is your 4s, 4s1, 4s2. But notice what happens after 4s. You get to the d orbitals. But this is not 4d, this is 3d. Again, we went from here 3p, not to d, not to 3d, but we went instead to 4s1. And then after 4s1, we went to 3d. So what you want to do is you want to be able to read electron configurations, okay? You want to read electron configurations based on the periodic table. And you want to remember the blocks. So let me go ahead and show you how that's done. Okay, that's your S block, that's your P block, that's your D block, that's your F block. So the best way to do electron configuration is through this acronym that I invented, NEVASP, NEVAS, where NE tells you the number of electrons, total number of electrons. VA tells you the valence electrons, how many valence electrons. The valence electrons, remember, are right here. All these have 5, all this have 4. The shell of the valence electrons, these are it right here. All these electrons, all these elements out here, the valence shell is the 4th shell right here. For these right here, the valence shell is the 6th shell. That's where the very last electrons are found. And then the previous noble gas, if you take an element like germanium, don't go to the closest noble gas, go to the previous noble gas, argon, okay? For something like antimony, the previous noble gas is krypton, not the closest noble gas. For iodine, the previous noble gas is krypton. So if you know how to find these things, in a periodic table, the number of electrons, the valence electrons, the shell, and the previous noble gas, then you can whip up the electron configuration, no problem. So we're going to do the electron configuration for sulfur. So for sulfur, Ne, number of electrons, is going to be, we know that this is 10, 11, 12, sulfur is right here. So the number of electrons is 10, 11, 12, 13, 14, 15, 16. That's 16 electrons total for sulfur, okay? This should have an atomic number 16 for sulfur. And the valence electrons, well, that's just 6. The shell of the valence electrons, well, that's just 3. And the previous noble gas of sulfur, that's just neon. So what's the electron configuration of neon? Well, I mean for sulfur, we know it's got a neon core. The reason why we're doing this is the shorthand notation, is because the inner core electrons aren't important. It's always the valence electrons that are important. So the neon core represents 10 electrons. Then let's just walk from neon to sulfur. From neon to sulfur, this is basically what's going on. Let me erase this real quick so that you guys can see what I'm doing. Again, this is electron configuration based on the periodic table. So if you walk from neon to sulfur, we go to 3s1, 2, okay, and then 3p1, 2, 3, 4. That's the electron configuration for sulfur. The electron configuration for sulfur is neon core, 3s2, 3p4, a total of 10 plus 2 plus 4 equals 16. 16 total electrons. Neon is the core. The valence electrons, 2 plus 4 is 6. And the valence shell is 3. Okay? Periodic table. That's the best way. Let me give you another example. Let's say that, and here's the summary of what I just did. Much more cleaner than my writing. So that's basically the summary of what I did. Let's do a more complicated, well, this is sulfur again. Again, I'm trying to show you different illustration of what's going on. That's your neon core, 3s2, 3p4. Okay, that's the electron configuration for sulfur. Let's do another, and your valence shell is going to be 6. I mean, your valence electron is 6 right here. That's for sulfur. Let's do the next one I want to do is scandium. Okay, let's do scandium. I'm gonna need to clear this. So scandium's right here. The previous noble gas is argon. And we put a bracket around that. And then we walk from argon to scandium. This is the fourth shell, 4s1, 2. And then we hit the 3D, and then it's 3D because this is your 3D. This is the starting. This is, you see, this is 4, but your shell number here is n-1. So this is a 3. N is 4. So this is a 3D1. That's the electron configuration for scandium. Again, you want to use the periodic table because that's the easiest way to do that. Here it is. That's basically your argon core. Right there's your argon core. And then 4s2, 3d1. And notice how I made this upside down. I'm making this upside down so that I'm trying to train you that it doesn't have to be always up or at the end. It could be somewhere in the middle. Could be somewhere in the middle. But it just needs to fill one of those. It just needs to fill one of those orbitals. Okay, so that's the electron configuration for scandium, a total of 21. Here we have a total of 18. This is 18 right here. 18 in argon, 19, 20 plus 1. That's 21 electrons for scandium. Let's do another one. Okay, let's do another one. This is tin. And again, let me, oops, sorry. I hate it when it does this. For tin, what we have is krypton is the previous noble gas. That represents 36. Okay, and then if we walk through, what we have is tin's not shown here. I wish I had the electron config, but if we did this, what we'll have is this is the inner core krypton, and then we go to 5s2, 4d10, and then 5p2. So this is your 5s2. This is your 4d10, and this is your 5p2. And so let's take a look at how that is determined from the periodic table. Previous noble gas is krypton. That's this right here. Your valence shell is 5. You're going to hit s orbital, 2 of them. Then you hit your d orbitals. That's 4d10, because all of these are completed. Then you hit back your p orbitals, and you go 1, 2. That's how you do the electron configuration using the periodic table, okay? If you want to do the electron configuration, say for rhenium, then rhenium would be previous noble gas is xenon. And then let's walk from xenon to rhenium. That's 6s2. And then what you have is the lanthanide series. The lanthanide series takes you to the bottom, and that's a 4f14. Okay, it takes you to the bottom, and then you pick up your d orbitals here. That'll be a 5d 1, 2, 3, 4, 5. Okay, so that would be the rhenium electron configuration. We have to introduce this 14 right here, because if you look at a regular periodic table, what you find is that from barium to lanthanum, you go to the bottom and you go to the lanthanide series. And if you march all the way across, there are 14 spots for the 14 electrons that fill these f orbitals. And then that's going to be at a 4s4 level, okay? So even though we're at the 6th shell, the D is 1 less than that, and the F is 2 less than that. So this is a summary of the first 20 electrons. And again, you could figure it out based on the mnemonic device, or you can do it based on the periodic table. So these are just exercises that you can practice on, but hopefully we've gotten through the worst part in terms of this particular section, how quantum mechanics relate to electron configuration, and how you can use the periodic table to get the electron configuration straight off. You don't have to memorize the filling order, because it's all laid out in the periodic table. Okay. One other suggestion, when you're trying to do the electron configuration of an ion, if you take a look at calcium, calcium has a total of, let me find my book real quick. Calcium has a total number of electrons of, I think, 20 electrons, okay? But if you're trying to do the electron configuration, say for calcium plus 2, that's 2 less electrons. So that has a total of electrons as 18. Look for the element with 18 electrons, and that's the electron configuration for calcium plus 2. The electron configuration for calcium plus 2 will be identical to argon, because argon has 18 electrons. So for these ions here, count the number of electrons, look for the element that has that number of electrons, and then write the electron configuration for that element. And now you have the electron configuration for the ions. It's going to be that somewhat that simplistic in terms of getting through this minefield.